Let's start with the introduction of filtration. Filtration is to separate suspended particulates from liquids or gases based on the filter medium, which allows the liquids or gases to flow through while holding solid particulates on the surface or within the medium, resulting a filter cake. Filtering principle is based on using a driving force, whether mechanical, gravitational, or applied under pressure or vacuum, to allow the fluid to pass through a porous material while leaving undesired particulates behind. Filter medium use varies depending on the application, and desired output influence the filtering rate, separation quality, and also filter durability. In this experiment, we focus on vacuum filtration. Vacuum filtration employs a vacuum as an external energy source to generate a pressure difference across the filter medium. The pressure differential works as a driving force, forcing the liquid through the filter while leaving the solid particles on its surface. The end result is a quick, efficient filtration process that yield a clean, filtrate, and well-defined filter cake. Faster and more efficient than gravity filtration, which is based entirely on gravitational force, making it excellent for applications requiring time and precision. There are also other filtration, for example, centrifugal filtration. It separates components by spinning the mixture at high speeds, forcing denser particles to migrate outward due to the centrifugal force. Cold filtration, on the other hand, involves cooling a solution to precipitate dissolved solids, which are subsequently filtered out. And we also have hot filtration, involves heating the solution, filter, and apparatus to prevent crystallization during the filtering process. This is particularly effective for solutions that are prone to crystal formation and could block the funnel or the other filtration equipment. The objectives of this experiment is to characterize the flow of a specific slurry or suspension mixture through the filter media and filter cake using the vacuum filtration technique, and to determine the specific cake resistance and the filter medium resistance to filtrate the flow at various vacuum pressure. Then the scopes of this experiment is plotting various filtrate flow rates over time, examining the relationship between the specific filter cake resistance and vacuum pressure, and also exploring the relationship between the specific filter medium resistance and vacuum pressure, and also calculating the specific resistance values for both the filter cake and filter medium.
Okay, now let's move on the theory of filtration process. Basically, filtration is separating particles from a liquid using a porous medium and then retaining the solids while allowing liquids to flow. This process relies on differential pressure across the filter medium as the driving force. And the common technique used in the filtration process are the cake filtration, where particles accumulate on the surface to form a filter cake. The second one is the deep bed filtration, where particles are removed from within the filter bed. And the next one is cross-flow filtration, where the particles are swept away by a flow perpendicular to the medium. For the mechanism of this filtration process, it employs a vacuum to create a pressure differential and then enhancing the filtration rate compared to gravity filtration. The components typically used in this process is a Baschner funnel or sintered glass, a vacuum pump, and a filter flask. The advantages of using this process is faster the processing time, and it is effective for separating solids and liquids in analytical and microbiological application. However, in the industry scale, there's might some challenge in handling larger volumes of fluid and solids because it requires higher pressures, larger filtration areas, and more robust equipment to sustain efficiency. Theoretically, there are two main resistances affect the process, which the first one is the cake resistance, or we call it RC. It increases with the thickness of the filter cake. And the next one is filter medium resistance, or we call it RM. It's initially dominant until the cake forms. The right-hand side equation is used usually to calculate the flow rate of the filtrate.
Equipment and material. The equipment required for the experiment includes an analytical balance, a burette, vacuum pump, power supply, conical flask, stopwatch, filter housing, glass rod, petri dish, thermometer, weighing dish, and a valve. For the material needed for the experiment are calcium carbonate, tap water, and filter paper. For the methodology, the first step is to accurately weigh 1.5 gram of calcium carbonate using a digital scale. And then the measured calcium carbonate is then added to 60 ml of tap water, and the mixture is thoroughly stirred using a glass rod to ensure uniform dispersion. After that, take the filter paper, and the filter paper will be weighed using an analytical balance, and the result will be recorded in the table. And then the two filter paper will be placed into the filter housing. To facilitate easy result recording, 5 ml of water will be carefully poured into the burettes. The vacuum pump and power supply will be turned on, and the valve will be adjusted to achieve the desired vacuum pressure of 200 mm mercury. Once the burette valve is closed, the mixture will be poured into the filter housing. By using stopwatch, the timing will be started once 4 ml of filtrate has been collected, and measurement will continue until a total of 55 ml is obtained or until the water level stabilizes. And then the filter cake along with the filter paper will be weighed using an analytical balance on the same petri dish. The surface area of the filter cake will then be measured and recorded. Next step is the filter cake along with the filter paper and petri dish will be placed in an oven at 105 degrees Celsius for 20 minutes. After 20 minutes, the filter cake will be taken out from the oven and separated from the filter paper, and both will be weighed individually using an analytical balance. Lastly, step 1 through 10 will be repeated at different vacuum pressure of 250 mm mercury and 300 mm mercury.
So after done the experiment itself, so during the experiment we have record some of the values, which is the volume of the filtrate and the time taken for each of the pressure to achieve that volume of filtrate. So this data can help with the results later. And before the experiment ended, we also have measured the mass of the wet cake before drying and after drying. Then afterwards, we use the data of the T over B and also the filtrate and make it into a graph. So this graph will be used for the calculation later. So after we plot the graph, we have the equation, which is the linear equation. So by using this linear equation, y equals to mx plus c, the m or the slope itself is the value of the kp over 2. So from here, the calculation we can find the kp value. So from the kp, we also calculated the cs and also have done the calculation using this formula. And out of this formula, we can find the alpha values, which is 1.5746 times 10 to the power 11 meter per kilogram. So next, based on the graph itself, we can obtain the B value by using the y-intercept. So the y-intercept acts as the B values in this equation. And by using B in this equation, we can find the Rm values. The Rm values for 200 mmHg pressure is 9.8254 times 10 to the power 9 meter to the power negative 1. And this calculation will be repeated for all the pressure, which is 250 mmHg and 300 mmHg, and further being discussed on the next part. Thank you.
So I'll continue with discussion. I'll start with the filtration behavior and theoretical alignment. The T over V versus V graphs confirm that the filtration process aligns with theoretical predictions. As the filtrate volume increases, the time per unit volume also rises due to the build-up of the filter cake, which increases resistance. We also observed that higher vacuum pressures lead to faster filtrations. For example, collecting 50 ml of filtrate took 48.98 seconds at 200 mmHg, but only 31.72 seconds at 300 mmHg. This is due to the stronger suction force at higher pressures, which speed up the liquid flow through the filter medium. As we increase the vacuum pressure, the mass of dry filter cake also increases. At 200 mmHg, the dry cake weighed 2.212 grams. At 250 mmHg, it increased to 2.597 grams, and at 300 mmHg, it reached 2.664 grams. This trend shows that higher pressure compacts the filter cake more effectively, reducing its porosity and forcing out more liquid. Additionally, the specific resistance of the cake rises with increased pressure, which indicates that the filter cake is compressible. On the other hand, the filter medium resistance decreases as pressure increases, making it easier for the liquid to flow through the filter. These combinations of changes enhance the overall filtration process. Looking at the T over V versus V graphs, we observe a steady upward trend which reflects the growing resistance as more filtrate passes through the system. This is due to the filter cake thickening over time. However, at high pressure, the slopes of these graphs become flatter. This flattening indicates improved filtration efficiency. Specifically, the steepest slope is observed at 200 mHg, showing the highest resistance, while the slope at 300 mHg is the flattest, demonstrating the most efficient filtrations. We also notice slight variations in the y-intercept of these graphs. These changes suggest that higher pressure slightly reduces the initial resistance before significant cake formation begins, further improving the flow of liquid through the system. Despite the overall success of this experiment, there are some experimental errors were observed. For example, uneven vacuum pressure adjustments, parallax errors when reading measurements, wind interference during mass measurements, and lastly, potential filter paper obstructions. There are some improvements can be made. The first one is align eyes perpendicular to scale to avoid parallax error. Use automated vacuum systems for consistent pressure. Conduct experiments in a wind-free environment, and last but not least, inspect filter paper for obstructions before use.
For conclusion, the T over V versus V graph for the three pressure settings exhibits a consistent upward trending, indicating an increase in the time per unit volume as the volume of the filtrate increases. This behavior aligns with the theoretical expectation of filtration processes, where the formation of filter cake progressively adds resistance to the flow of the liquid itself. Then, the result in Table 1 indicate that the higher vacuum pressure leads to a faster filtration rate. Then in Table 2, it shows the difference in the mass of the wet and dry cakes of varying pressures. It shows pressures increase, the mass of the dry filter cake also increases. So, and also some experimental factors such as uneven vacuum adjustments or fluctuation in pressure settings, parallax errors in the glass tube may have introduced inaccuracy, and also wind interference during the weighting of calciums, carbonate, and filter paper may have affected the measurement due to the sensitivity of the electronic mass balance. Then the observer's eyes should be positioned perpendicular to the scale to minimize parallax error. Automated vacuum filtration systems are recommended to ensure the consistent pressure settings throughout the experiment, and the experiment should also be conducted in a controlled environment. So these are the control measures that to minimize the errors and also inaccuracy. So all in all, the experiment was successfully demonstrated the effect of varying vacuum pressure on the filtration process. Higher pressure facilitated faster filtration rates. It also a greater compaction of the filter cake, consistent with the theoretical expectation. Therefore, even though the minor experimental error were noted, implementing the recommended precaution will help minimize this issue in future experiments. That's all from us. Thank you.